I want you to picture something for a second. Like, really close your eyes, if you're in a place where you can safely do that, obviously, and transport yourself back to the first few days of September.
Right.
Specifically, September in the year 1859.
Oh, man, what a time.
Yeah. So imagine you are fast asleep. It's the middle of the night, maybe 1 or 2 in the morning. But suddenly you wake up, you're blinking, completely disoriented, because your bedroom is it's flooded with light.
Like daylight.
Exactly. So you step outside, your heart is pounding, and you're fully expecting to, I don't know, a barn on fire, or maybe the neighboring town burning down, or perhaps you think you've somehow slept through the entire night and it's already morning.
Which would be confusing enough.
Right. But it isn't morning.
Ah.
And absolutely nothing is on fire. You look up, and the sky itself is glowing.
And it's not just a faint ethereal glow either. The historical records we have from that night describe a level of brightness that entirely defies the natural rhythm of the night. I mean, we're talking about a sky so luminous, so bathed in this weird atmospheric light that you could literally stand in your front yard at midnight and read the fine print of a newspaper.
Just by the light of the sky.
Simply by the illumination coming down from the heavens, yeah.
Which is such a striking, surreal image to me. And the thing is, this wasn't just some isolated phenomenon happening in one quirky little corner of the globe.
No, it was everywhere.
Right. Like over in the Rocky Mountains, there are these encampments of gold miners. And these are rugged guys who live entirely by the rhythms of the sun. They don't have alarm clocks, you know?
Right. Sun goes up, they work. Sun goes down, they sleep.
Exactly. So on this specific night, they roll out of their bunks, they look up at this brilliant glowing sky, and they actually start gathering kindling.
That's amazing.
They start cooking breakfast, they pour their coffee, they are absolutely certain that dawn has broken over the mountains.
And you can't blame them.
No. But the sky isn't just bright, it's bursting with color. We're talking about auroras, what we typically call the northern lights.
Which is usually a phenomenon strictly confined to, the freezing high latitudes.
Yeah, the Arctic or the Antarctic.
Right. But on this night, in 1859, the sky is rippling in these curtains of brilliant red and green fire over the tropics.
The tropics.
Yeah. People are standing under palm trees in Cuba, in Colombia, in Hawaii, just looking up at a sky that has turned into an ocean of neon fire.
It sounds incredible.
It is. By all accounts from the diaries and the newspapers of the time, the most beautiful thing anyone alive had ever witnessed.
I mean, I would be terrified, but also entirely mesmerized.
Totally. It was a moment of absolute breathtaking wonder. It's really rare in history to find a global phenomenon that unifies humanity in a shared experience of sheer awe, but this was undeniably one of them.
Right.
For the vast majority of the global population, it was almost a religious or spiritual spectacle.
But, and there is a massive but here.
Oh, yes.
If we look just slightly beneath the surface of that wonder, there's a much darker, much more dangerous story playing out simultaneously.
A very eerie flip side.
Yeah, this completely terrifying flip side to the beautiful light show. Because while the everyday person, the farmer or the miner, was looking up at the sky in wonder, the people operating the cutting-edge technology of the era were experiencing an absolute nightmare.
And we are talking about the telegraph operators.
Exactly. In 1859, the telegraph was the absolute pinnacle of human engineering. It was basically the silicon chip of the Victorian era. And on this beautiful, glowing night, those telegraph machines were going completely haywire.
The accounts from the telegraph offices across North America and Europe they're incredibly dramatic, almost chaotic.
Yeah, what was actually happening to them?
Well, you have these professional operators sitting at their desks, entirely accustomed to the rhythmic tapping of their machines, right? And suddenly they're getting violently shocked by their brass equipment.
Like actual physical shocks.
Yes. Sparks are literally flying off the transmission keys. And the specialized paper, the long, continuous strips they use to record the incoming dots and dashes of the Morse code.
Oh, right, the ticker tape stuff.
Exactly. That paper is spontaneously bursting into flame right on their desks.
Which is insane. Your office equipment is just catching fire.
And then the most impossible, mind-bending thing of all happens.
This is the part that gets me.
Right. So the operators, trying to stop their offices from catching fire and, trying to stop getting electrocuted, do the most logical thing a technician can do.
They unplug it.
They completely physically disconnect the power source from the telegraph lines. They unplug the batteries, and the machines keep working.
Unbelievable.
The operators find themselves sending and receiving messages across hundreds of miles with the batteries entirely unplugged.
Which, I mean, that was a profound paradigm-shifting moment in human history, wasn't it?
Oh, absolutely. Those copper wires strung between cities were no longer running on human-generated electricity. For the very first time, human infrastructure had been completely hijacked.
Hijacked by the sky.
Right. The lines were running entirely on the invisible energy of the cosmos.
And that bizarre, terrifying reality brings us to the mission of our deep dive today. We are going to explore the largest solar storm in recorded history.
An event that astrophysics now refers to as the Carrington Event.
The Carrington Event. But listen, we aren't just looking backward at some quirky historical curiosity today, or like an entertaining 19th century anecdote.
Absolutely not. What we are looking at is cosmic rehearsal.
A drill.
Yes, the universe was running a drill. Our goal for you, the listener, is to understand how the most beautiful night in human history was actually a warning shot from the cosmos.
We need to explore the underlying physics of what actually happened, and most importantly, we need to understand why the exact same event, if it were to happen tonight,
Could quite literally switch off the modern world.
Okay, let's unpack this. And I want to do that by going directly to the man who gave this event its name.
Richard Carrington.
Yes, because to understand the scale of what happened, we need to travel to the morning of September 1st, 1859. This is roughly 18 hours before the sky caught fire.
Right.
I was reading up on Carrington, and the setting of his discovery is just so uniquely Victorian.
It really is. Richard Carrington was a young English astronomer. He was in his early 30s at the time. And you have to remember, in 1859, astrophysics as we know it today didn't really exist.
It was a very different science.
Exactly. Astronomy was still very much a hands-on observational science. It was about mapping, timing, taking notes, and sketching.
And Carrington had the means to do this.
Really?
He was wealthy.
Yes, he was independently wealthy, the son of a brewer, actually,
Yeah.
which allowed him to build his own private observatory at his estate outside London. And he was deeply, almost obsessively focused on studying the sun.
But he wasn't just like staring through a telescope directly at the sun, right?
Right.
Because that would obviously blind you.
No, he had a very specific, very safe method. On this particular morning, a Thursday, he was doing what he did every single sunny day. He was using his telescope to project a highly magnified image of the sun onto a large, specially coated glass screen in his observatory.
Oh, so it's like a projector.
Exactly. This allowed him to safely look at the projection and meticulously sketch the positions and shapes of the sunspots.
Those are the dark, relatively cooler patches on the solar surface.
Right.
I always picture him in this quiet, dusty, sunlit room, completely isolated from the noise of the world outside, just lost in this meticulous, almost meditative work of tracing these dark blemishes on a glowing circle. It's a very peaceful image.
It was a scene of total academic tranquility.
Right up until it wasn't.
Right up until exactly 11:18 a.m. That is the exact moment when the unprecedented happened.
What did he see?
As Carrington was leaning over his sketch, something completely alien appeared on the projection. He saw 2 points of blinding, intensely bright white light suddenly erupt from within the massive sunspot group he was currently drawing.
And these weren't just like slightly brighter patches. I actually read his original report to the Royal Astronomical Society, and he noted that the light was so intense it completely washed out the image of the sunspots themselves.
It was overwhelming.
To use an analogy, it's like you are sitting there staring at a calm, predictable campfire, right? Maybe you're sketching the shape of the charred logs. And suddenly, without any warning whatsoever, there is an atomic flash right in the middle of the embers.
That is a very fitting analogy.
You are witnessing something enormously powerful, but you lack any scientific context to understand what it actually means.
Carrington was completely taken aback. In fact, his immediate reaction wasn't, I have discovered a new solar phenomenon.
What was it?
His first thought was actually that a ray of unfiltered sunlight had somehow pierced through a crack in his observatory roof and was shining directly onto his projection screen.
Really? He thought his roof was leaking light.
He physically moved the telescope to check.
Which is such a human reaction. Oh, my equipment must be broken.
Exactly. But once he realized the blinding white kidney-shaped flashes were moving with the sun's image, he knew he was witnessing something real, and he panicked slightly.
Understandably.
He realized he was seeing something no human had ever documented, so he actually ran out of the observatory to find a witness.
But by the time he came back with someone, it was over, right?
Yes, the entire visible event lasted only about 5 minutes. Carrington had become the first human being to ever witness and record a solar flare as it happened.
Wow.
But, as you pointed out with your campfire analogy, he had no context. In 1859, the scientific understanding of the sun was incredibly rudimentary. We didn't know about nuclear fusion. We didn't really understand what a sunspot was.
So he just saw the flash.
Right. Carrington saw this massive release of energy, this blinding flash, but he didn't know what it meant for the Earth. He didn't know the physical mechanisms behind it. He just knew he had seen a solitary, extraordinary anomaly.
And to really grasp the irony of this specific moment in time, we have to pull the camera back and look at the world Carrington was living in. The world humming along outside his quiet observatory.
Yes, the 1859 stage.
Because 1859 wasn't just any year. It was a very specific inflection point in human history.
It was absolutely crucial timing. This was the dawn of the Wired Age. The world was newly, albeit very thinly, electrified. We were just stepping into our reliance on invisible currents.
It's the era of the telegraph, which people often call the Victorian internet. And that's not really an exaggeration, is it?
Not at all. I mean, the telegraph fundamentally, irreversibly altered the human experience of time and distance. Think about it. For the entirety of human history up to the 1840s, a message could only travel as fast as a physical object could move.
Right, like a letter on a train.
Exactly. It could only go as fast as a horse could gallop, a ship could sail across an ocean, or a steam train could ride the rails. If an event happened in London, it took weeks for New York to find out. Yeah. But suddenly, with the widespread adoption of the telegraph by the late 1850s, a thought, a piece of news, or a financial transaction could be sent across a continent in a matter of minutes. It was a complete revolution in communication.
So humanity in 1859 is feeling pretty incredibly proud of itself. We've strung these copper wires on wooden poles across the American frontier. We're laying cables underwater. We're sending these invisible electrical pulses to communicate. We really feel like we are mastering the raw forces of nature.
A lot of hubris, yeah.
And meanwhile, up in his little observatory, Carrington is frantically sketching this blinding flash of light. The dramatic irony here is staggering to me. While the telegraph operators in Boston and New York are tapping away at their keys feeling like absolute masters of the universe, a massive, invisible, apocalyptic-level threat has just been unleashed.
And it is hurtling across the 93-million-mile gap between the sun and the Earth.
And absolutely nobody on the planet knows they should be afraid.
The disconnect between the sheer, unimaginable scale of what the sun had just done and humanity's complete unawareness is chilling. Because that blinding flash Carrington saw the solar flare was merely the visual component.
Just the light.
Right. It was just the light of the explosion traveling at the speed of light, reaching Earth in about 8 minutes. It was harmless in and of itself. But behind that light, something much heavier, much denser, and infinitely more dangerous had been violently ejected into the vacuum of space, and it was racing directly toward us.
Which brings us to the speed of this thing.
Yeah.
Because it wasn't just a threat, it was a ridiculously fast-moving threat. I dug into the timeline between Carrington's sketch at 11:18 a.m. on September 1st and when all hell broke loose on Earth in the early hours of September 2nd.
Yes, the transit time.
How quickly did this cosmic payload actually cross that 93-million-mile gap?
The velocity of the solar matter ejected during the Carrington era is one of its most freakish defining characteristics. It crossed the vast distance from the sun to the Earth in roughly 17.6 hours.
Okay, I need to stop you there and push back a little because we need to put that speed into perspective. Because to a layperson, 17.6 hours sounds like a long time. It's a long time to sit on an airplane or wait for a package. But for crossing the inner solar system, how fast is a 17.6-hour transit compared to normal, everyday solar weather?
Good point. To give you a proper sense of scale, the sun is constantly blowing a stream of particles toward us. We call that the solar wind. A typical eruption from the sun, a standard solar storm, usually takes several days to reach Earth.
Like how many days?
Often anywhere from 2 to 4, sometimes up to 5 days. It's a massive cloud of particles, but it has to push its way through the ambient solar wind, like a ship pushing through water.
Right, there's resistance.
Exactly. But the Carrington event cut that transit time down to less than a single day.
So, to go back to analogies, if we imagine the sun as a pitcher throwing a baseball, normally when the pitcher throws a curveball, you can watch it arc through the air, you see the trajectory, and the catcher has time to read the spin, shift their weight, and ready the mitt before the ball arrives.
Right.
But a 17.6-hour transit from the sun, that's like the pitcher releasing the ball, and it violates the laws of physics and violently slams into the catcher's mask a microsecond later. It completely breaks your intuitive sense of scale and distance. It's a cosmic bullet.
The cosmic bullet analogy works to convey the shock, but with one terrifying caveat.
What's that?
It wasn't just a small, dense projectile. It was more like a cosmic snowplow.
A snowplow.
Yes. The sheer velocity implies a violent, unimaginably powerful expulsion of energy. It was moving so incredibly fast, estimated at over 5 million miles per hour, that it was essentially bulldozing all the ambient solar wind out of its way.
Wow.
It was compressing the space ahead of it, creating this massive interplanetary shockwave as it raced toward Earth.
And when that shock wave and the matter behind it finally hit us, it didn't just quietly wash over the atmosphere. It put on a show that stopped the entire planet in its tracks.
It really did.
I want to go back into those global reports from the general public because the level of pure, unadulterated wonder people experienced is hard to overstate. It wasn't just a scientific anomaly. It was a huge cultural event.
Absolutely. The focus for the general public was entirely on the visual spectacle. Like we mentioned earlier, auroras were seen in the tropics, which is astronomically rare, but the effects were ubiquitous across all latitudes.
I read some wild stuff about the Northeast U.S.
Oh, yeah. People in the northeastern United States reported that the night sky was so luminous, bathed in these pulsating waves of blood red and emerald green light, that it began to severely interfere with the natural behaviors of wildlife.
Yes, the reports about the birds. I found several historical accounts from New England where people noted that birds began to sing their morning choruses in the middle of the night.
They were just totally confused.
The sky was so bright, and the quality of the light was so eerie and pervasive, that the birds were completely fooled into thinking it was dawn. You had roosters crowing at 2 a.m.
What's fascinating here is the profound duality of the event.
Say more about that.
Well, on the one hand, you have the everyday person, the farmer in Ohio, the merchant in London, the miner in Colorado, experiencing a moment of transcendent, poetic beauty. They are watching a celestial light show unlike anything seen before or since. It feels miraculous. It feels like a blessing from the heavens.
Right.
But simultaneously, hidden directly behind that glowing sky, the exact same event is doing something deeply sinister. It was the very first time the cosmos reached down into human infrastructure and decided to run our machines on its own terms.
That duality is everything. It's the entire story. The everyday person is standing on their porch, marveling at the sky, holding a newspaper up just to see if they can read the headlines in the glowing night, feeling like they've been given a gift.
Yeah.
But the true, terrifying reality of what was actually happening was completely invisible to them. It was only visible to a very small, highly specialized group of people who were literally wired into the global network.
The telegraph operators.
Right. Let's dive into that. Let's detail the absolute chaos in the telegraph offices, because this wasn't just a matter of the lines going a little staticky or like messages getting garbled. This was violent and dangerous.
Extremely dangerous.
I read an account from an operator in Washington, D.C., who said his forehead accidentally brushed a ground wire, and an arc of electricity leaped out and struck him so hard it stunned him.
Ouch.
Yeah. Operators were physically being knocked out of their chairs by electric shocks surging through their equipment.
The accounts are uniform in their description of extreme electrical anomalies.
Yeah.
The telegraph wires themselves were sparking wildly at the terminals, and remember the physical environment of these offices.
Oh, lots of wood and paper.
Exactly. They were filled with specialized, chemically treated paper, the long, continuous strips that ran through the receiving machines to record the indentations or ink marks of the Morse code.
Right.
That paper was spontaneously combusting. The electrical current surging through the telegraph lines was generating so much intense heat at the brass receiving instruments that the paper literally burst into open flame on the desks.
It's like a scene from a science fiction horror movie. The mundane machine you work with every single day, the literal tool of your trade, suddenly turns into this sparking, flaming hazard with a mind of its own.
It's terrifying.
But then we reach the peak detail of this entire event, the moment that sounds less like a historical fact and more like a ghost story. The operators are trying to manage these literal fires. They're trying to avoid these violent shocks, so they do the obvious, safe thing to cut the power.
They disconnect the batteries.
Right.
Specifically, they were using massive racks of what were called Daniel cells. These were glass jars filled with chemicals that provided the direct current for the lines.
Right, so they physically unhook the wires from these chemical batteries. The machines should be dead. They should be inert, lifeless pieces of brass and wire sitting on a wooden desk.
But they aren't.
No. The operators discovered that with the batteries entirely disconnected, the lines still work. And not just barely. They work incredibly well.
Better than normal in some cases.
I actually read a transcript of a literal conversation between an operator in Boston and an operator in Portland, Maine. They both confirmed over the wire that their batteries were completely disconnected, and they continued to send messages back and forth for nearly 2 hours, powered entirely by the aurora.
It is one of the most stunning testaments to the raw power of the event.
But here's where it gets really interesting, and where I need you to break down the science for me. Because reading that historical account, it broke my brain a little bit.
Sure.
Wait, how does a literal, physical copper wire transmit an intelligent message without a power source attached? It sounds like magic. How do you send a pulse of information down a wire when there is no battery pushing the electrons?
It sounds like magic, but it is pure fundamental physics. Specifically, it's the science of induced currents, governed by Faraday's law of electromagnetic induction.
Okay, induced currents.
Right. To truly understand this, we have to look at the deeply intertwined relationship between magnetism and electricity. They are not separate forces, they are two sides of the same coin. Electromagnetism.
Okay.
If you take a magnetic field and you change it, say, if you physically move a magnet back and forth near a wire, or if you cause the strength of a magnetic field to rapidly fluctuate, that changing magnetic field will literally push electrons through any nearby conductor, like a copper wire. It induces an electrical current.
So the changing magnetic field essentially acts as an invisible battery.
Precisely. The fluctuation is the power source.
Wow.
Now, zoom out from a simple wire and a magnet and apply this to the Carrington Event on a planetary scale. The Earth itself is a giant magnet.
With a north and south pole.
Exactly. It has a massive magnetic field that extends far out into space, generated by the churning of liquid iron in the planet's core. When this massive solar storm hit the Earth, it didn't just quietly brush past us in the upper atmosphere. It violently, brutally compressed and distorted our planet's magnetic field.
So it shook the Earth's magnetic field.
It made the Earth's magnetic field fluctuate wildly and rapidly.
Okay, I'm tracking. And the telegraph wires, which humanity had proudly strung up for hundreds of thousands of miles across the surface of the Earth, they acted like giant antennas picking up those magnetic fluctuations.
Exactly. The telegraph lines were essentially massive, continent-spanning copper loops. The rapidly changing, wildly fluctuating magnetic field of the Earth induced massive electrical currents within those long telegraph wires.
That is just wild.
The wires weren't running on the small chemical Daniel cells in the telegraph offices anymore. They were quite literally running on the fluctuating magnetic power of the star in the sky. The Earth's distorted magnetic field was acting as a planetary-scale electrical generator, pumping massive amounts of electricity directly into human infrastructure.
That is mind-blowing. It really puts human engineering into perspective.
Yeah.
So synthesizing all of this, the telegraphs acting possessed wasn't magic, and it wasn't ghosts in the wires. It was astrophysics.
Pure astrophysics.
It was the fundamental laws of electromagnetism playing out on a terrifying cosmic scale. But that raises the ultimate question, the piece of the puzzle Carrington was missing. What exactly did the sun throw at us? What was the actual physical mechanism that Carrington saw as a flash of white light and that arrived 17.6 hours later to set the sky on fire and possess the telegraph lines?
What the sun threw at us is a phenomenon known in modern astrophysics as a coronal mass ejection, or a CME.
A CME. Let's break down the anatomy of a CME, because I think a lot of people, they conflate a solar flare with a solar storm. But a CME is not just a beam of light or a wave of heat.
The distinction is critical. A solar flare, which is the flash of light Carrington saw, is simply a sudden, intense burst of electromagnetic radiation light, X-rays, UV rays. It travels at the speed of light.
Okay.
But a CME is something much more physical, much more substantial. It is a massive eruption of actual solar matter. Specifically, it is a billion-ton cloud of magnetized plasma violently flung off the outer atmosphere of the sun, known as the corona.
Magnetized plasma. That sounds like something out of Star Trek. Break that down for us. What does it actually mean for a cloud of gas to be a magnetized plasma?
Well, plasma is often called the fourth state of matter.
Yeah.
If you take a gas and you heat it to extreme temperatures, we're talking millions of degrees, the energy is so intense that the electrons are physically stripped away from the atomic nuclei.
Okay, so the atoms are falling apart.
Right. You are left with a chaotic soup of freely moving, electrically charged particles, negatively charged electrons, and positively charged ions.
Got it.
And here is the crucial part. Because these particles are electrically charged, as they move, they generate and carry their own embedded magnetic field.
Oh, I see.
So imagine a billion-ton cloud of this intensely hot, highly charged soup carrying its own massive internal magnetic field, exploding off the sun and hurtling through the vacuum of space.
Right toward us.
When it finally reaches Earth, it doesn't just hit the physical atmosphere, the air we breathe. It slams directly into Earth's own invisible magnetic field, the magnetosphere.
So it's a collision of two massive magnetic forces in the vacuum of space.
Exactly. And the physics of that collision is what causes the profound global disruptions we call a geomagnetic storm.
I was trying to picture this collision, and I keep thinking of the Earth's magnetic field like a planetary-scale airbag.
An airbag.
Yeah, it's this invisible protective shield that normally deflects the everyday ambient solar wind around the planet, keeping our atmosphere from being stripped away. But when a CME of the Carrington magnitude hits, it's like that airbag deploying during a head-on collision with a freight train moving at 5 million miles an hour.
The airbag analogy works to visualize the protection, but with one terrifying difference.
What's the difference?
When a car's airbag deploys, it absorbs and dissipates the energy to protect the passenger, but magnetic fields are elastic. When the Earth's magnetic field is compressed that violently by a CME, it actually acts more like a slingshot.
Wait, a slingshot? How so?
It's a process called magnetic reconnection.
Right.
The sheer kinetic force of the billion-ton plasma cloud crushes the Earth's magnetic field inward on the day side, facing the sun. But the magnetic lines of force don't just compress, they are stretched out behind the Earth like a massive tail.
So they're getting pulled back.
Right. Eventually, the tension becomes too great. The magnetic lines snap, break, and reconnect in new configurations. And when they snap back, they release immense amounts of stored energy, violently accelerating charged particles down the magnetic field lines directly toward the Earth's magnetic poles. That snapping back, that slingshot effect, is what funnels the massive amounts of energy down into our upper atmosphere.
And when those highly energized particles smash into the oxygen and nitrogen in our atmosphere, they light up like a neon sign, which creates the auroras.
Exactly.
And because the storm was so violently powerful in 1859, the auroral oval, which usually sits quietly over the Arctic, was pushed all the way down to the equator, creating the blood-red skies over Cuba and Hawaii.
Precisely. You are seeing the physical manifestation of the Earth's magnetic field violently struggling to absorb and redirect the energy of the sun.
The slow, agonizing unveiling of this scientific knowledge over history is fascinating to me. Because in 1859, the scientific community couldn't fully comprehend this sequence of events.
Not at all.
Carrington saw the flash. The world saw the auroras. The telegraph operators felt the shocks. But putting those disparate pieces together into a coherent causal model of a coronal mass ejection, taking 17.6 hours to hit Earth's magnetosphere and induce currents, they just didn't have the pieces of the puzzle yet.
It was a subject of intense, sometimes bitter debate. Carrington himself cautiously suggested a connection between his solar flare and the subsequent magnetic storm on Earth, but he lacked the theoretical framework to prove it.
People didn't believe him.
In fact, Lord Kelvin, one of the most prominent physicists of the 19th century, vehemently denied that the sun could possibly exert magnetic influence over the Earth. He argued it would require an impossible amount of energy.
So the greatest physicist of the age basically said, "No, Carrington, you're crazy. It's just a coincidence."
Exactly. It took the next century of scientific advancement to slowly figure out the actual mechanics. It required a deeper understanding of plasma physics, the definitive discovery of the solar wind in the 1950s, the realization that the Earth even has a structured magnetosphere, and eventually the dawn of the space age and the ability to launch satellites to actually observe these CMEs as they leave the sun and track them through space.
So in 1859, humanity was observing the dramatic symptoms without having any concept of the disease.
That's a great way to put it.
And here is where we hit a crucial, deeply uncomfortable truth about our history. We look back at 1859. We read the quaint stories of the gold miners cooking breakfast at midnight. We marvel at the beautiful auroras over the tropics, and we chuckle at the quirky stories of unplugged telegraphs sending ghost messages.
It's charming, in a way.
Right, it feels like a harmless wonder. We survived the Carrington event, but we need to be very, very clear about why we survived it.
Yes, this is the pivot point of the entire discussion.
Why did we survive?
The reason humanity survived the Carrington event relatively unscathed wasn't because we had robust, brilliant defenses. It wasn't because our technology was incredibly resilient or cleverly engineered to withstand space weather.
Right.
It was simply because we had almost nothing to break.
The 1859 safety net was our own technological infancy. The greatest defense humanity had during the largest geomagnetic storm in recorded history was the fact that we were, compared to today, practically primitive.
Consider the state of human infrastructure in the mid-19th century. We had strung up a few thousand miles of copper telegraph wires, and we had some racks of chemical batteries. That was the absolute total extent of our electrical infrastructure.
That's it.
If a telegraph station caught fire, it was a local, isolated problem. The operator puts out the fire with a bucket of water, they replace the burnt paper, they rewire the key, and eventually, a few days later, the storm passes and they go back to work.
Because the core functions of society, the things that kept people alive, were completely insulated from electromagnetic forces.
Yeah.
Food production relied on horses, plows, and human labor. Water transport relied on gravity or manual hand pumps. Heating relied on cutting wood or burning coal. Lighting relied on whale oil or kerosene. The entire machinery of civilization was physical, mechanical, and entirely unelectrified.
There is a massive, almost tragic irony there. The sheer lack of sophisticated technology is precisely what saved humanity from a technological disaster. If we connect this to the bigger picture, the Carrington event was a harmless wonder only because of the highly specific moment in history when it happened.
Right, it slipped through a tiny window in human history.
Exactly. If that exact same billion-ton cloud of magnetized plasma had hit the Earth 100 years later in 1959 at the dawn of the space age and widespread electrification, it would have been a massive crisis.
And if it were to hit 160 years later, today,
it would be a very different story. It would be a global, civilization-altering catastrophe.
So what does this all mean for us, for you listening right now? It means we survived 1859 because we were primitive. But we are no longer primitive. We have completely, systematically abandoned the safety net of 1859.
We have spent the last century and a half meticulously building a world that is fundamentally, inescapably dependent on the very systems a Carrington-class event is uniquely equipped to destroy.
Which means we need to pivot from the past to the present. If 1859 was a rehearsal on an empty stage, what happens when the exact same cosmic storm hits a fully built, highly electrified, deeply interconnected world today? Let's walk this forward concretely, step by step.
Okay.
The sun erupts, the cosmic bullet hits the planetary airbag, the slingshot effect triggers, and the magnetic field fluctuates wildly. What does a Carrington-class CME actually do to modern infrastructure?
The primary threat is driven by the exact same mechanism that possessed the telegraph lines in 1859, induced currents. But today, we don't just have a few isolated low-voltage telegraph wires connecting major cities. We have millions upon millions of miles of high-voltage electrical transmission lines wrapping the globe. These lines span entire continents. And because of their massive length, they act as incredibly efficient, perfectly designed antennas for catching those rapid magnetic fluctuations.
So instead of a little Stark in a telegraph office or a piece of paper catching fire, what happens when these continental antennas pick up the storm?
Massive, unwanted, uncontrolled electrical currents, specifically geomagnetically induced currents, or GICs, surge through the global power grid. And here's where the engineering becomes critically important.
Tell me about the engineering.
The modern power grid is designed to operate on alternating current, or AC. It relies on a very specific, delicate frequency, usually 50 or 60 hertz, and precisely controlled voltages.
Right.
But the currents induced by a solar storm are essentially direct current, or DC. It is a slow, massive influx of DC power pushing its way into an AC system.
And the grid isn't built to digest that.
Not at all. When these massive, chaotic DC currents flow through the transmission lines, they seek the path of least resistance to the ground. And unfortunately, that path goes directly through the most critical, expensive, and vulnerable components of the entire grid.
Which are?
The high-voltage transformers.
Let's focus on transformers for a second. These are the massive, blocky metal boxes you see at electrical substations, right?
Yes.
The things that step power up to high voltages so it can travel hundreds of miles and then step it back down so it doesn't blow out the appliances in my house.
They are the beating hearts of the electrical grid. They work by using alternating current to induce magnetic fields within their heavy iron cores, transferring power from one coil of wire to another.
Okay, so they're already dealing with magnets.
Exactly. But when a massive influx of direct current from a solar storm enters a transformer, it shifts the magnetic operating point of the iron core. It causes a phenomenon called half-cycle magnetic saturation.
Okay, half-cycle magnetic saturation. What does that actually mean in practical terms?
It means the core of the transformer can no longer contain the magnetic flux. The energy spills out of the core and into the structural steel of the transformer itself.
That sounds bad.
It is. The steel begins to heat up incredibly rapidly. We're talking about hundreds of degrees in a matter of minutes. The heavy copper windings inside can literally melt from the inside out. The insulating oil that fills the transformer can boil, produce explosive gases, and catch fire.
So the solar storm literally melts the beating heart of the grid from the inside.
Yes.
What's the immediate consequence of that happening across hundreds of substations simultaneously?
Well, the grid is designed with protective relays. In a best-case scenario, the grid senses the massive anomaly and protects itself by automatically shutting down, severing the connections to save the hardware.
Yep.
In a worst-case scenario, the protective relays fail or are overwhelmed, and the transformers themselves physically burn out and are destroyed.
Yeah.
But either way, the immediate result is the same. You are looking at continent-scale blackout.
Continent scale.
Not just a city losing power for a few hours due to a thunderstorm, but massive interconnected regions of the globe going completely dark simultaneously.
And if the transformers physically melt,
Mm-hmm.
turning the power back on isn't like flipping a circuit breaker in my basement.
Not even remotely. These high-voltage transformers are not off-the-shelf items. They are massive, custom-built, highly specialized pieces of equipment that can weigh hundreds of tons. They cost millions of dollars each.
So you can't just run to the hardware store.
No. They take months, sometimes over a year, to manufacture. And the global supply chain does not have thousands of them sitting in warehouses waiting to be deployed. If a significant percentage of them across a continent are physically destroyed by a solar storm, rebuilding the grid isn't a matter of days. It could take months or even years to restore full power to certain areas.
And that leads us to the terrifying domino effect. Because in the modern world, electricity isn't just about keeping the lights on so you can read at night. It's the foundational layer of literally everything else we rely on.
Absolutely everything.
If the foundation cracks, the whole house comes down. I want you to detail everything downstream of electricity that goes with it.
Well, the modern world is what systems engineers call a tightly coupled system. Everything depends on everything else. If you lose the electrical grid for an extended period, weeks or months, the cascading failures are catastrophic. First, you lose global communications.
The internet.
The internet, cell phone towers, fiber optic repeater stations, the massive server farms processing data, they all require constant, massive amounts of power and, crucially, cooling.
But don't those critical facilities have backup diesel generators?
They do, but backup generators only have fuel storage for a few days, maybe a week. Once the diesel runs out, how do you get more? The fuel distribution network relies on electric pumps at refineries, electric pumps at gas stations, and a digitized supply chain to tell the trucks where to go.
Oh, wait.
If the grid is down, the fuel stops moving. When the generators die, communication ceases.
And it's not just ground-based comms, right? What about GPS?
GPS is incredibly vulnerable. A Carrington-level storm produces immense amounts of radiation that could permanently damage or degrade the satellites in orbit. But even if the satellites survive the radiation, the ground stations that correct their orbits, upload data, and distribute the incredibly precise timing signals require power.
What happens if GPS goes down?
Without GPS, global aviation is grounded. Maritime shipping logistics dissolve. And perhaps most critically, the precise timing mechanisms required to synchronize the global financial sector begin to fail. Global banking grinds to a halt. You can't process digital transactions, you can't access ATMs, you can't manage just-in-time supply chains for grocery stores.
I want to pause here and highlight a very specific visceral detail for you, the listener. Because when we talk about this stuff, it's easy to get lost in the grand abstraction of global banking failures or disrupted supply chains. It feels like a movie plot.
It does.
But if the power grid goes down for months, the reality is much more local and immediate. If the grid goes down within a few days, you can't even flush the toilet in your own home.
This raises an incredibly important point about our fundamental survival needs and how insulated we are from the mechanisms that provide them.
Exactly. Explain to us why.
Yeah.
Why does a solar storm hitting the Earth's magnetic field mean my bathroom stops working?
Because modern urban water systems are entirely artificial, and they rely entirely on massive electric pumps. Getting fresh water from a distant reservoir or a river, pushing it through a high-tech water treatment plant, and then pumping it up into the municipal water towers that provide the hydrostatic pressure to push water out of your faucet. All of that requires massive, continuous amounts of electricity.
And the sewage.
Processing the resulting wastewater at sewage plants requires electricity. If the grid is down for weeks, the reservoirs run dry, the pressure drops to zero, the water simply stops flowing, you can't drink, you can't wash, and you can't flush.
That's horrifying.
A modern, densely populated city without running water or sewage processing becomes uninhabitable in a matter of days due to the risk of disease alone.
It's a terrifying cascade of fragility. No power means no water. It means no fuel pumps. It means no grocery store refrigeration, leading to immediate food spoilage. It means no communication with emergency services. It's the rapid, systematic unwinding of modern civilization back to the 19th century, but with none of the 19th century infrastructure or skills to support the population.
Precisely.
And the financial toll of this kind of unwinding is almost impossible to comprehend.
Researchers, governments, and major insurance organizations have attempted to model the economic impact of a Carrington-class event hitting the Earth today. The modern damage projections for this kind of severe geomagnetic storm run anywhere between $0.6 trillion and $2.6 trillion in the United States alone.
Trillion, with a T.
Yes. Trillions of dollars. Globally, the numbers are simply staggering. And it is vital to emphasize that these are just projections. They are estimates based on complex models of grid vulnerability and economic interconnectedness.
Sure, but still.
But they give us a sobering sense of the sheer scale of the potential disaster. It would be an economic shock unlike anything in modern history, dwarfing natural disasters like hurricanes or earthquakes, because the impact would be simultaneous across entire continents.
I listened to all of this, the melting transformers, the loss of running water, the collapse of global logistics, the multi-trillion-dollar price tag, and I have to play devil's advocate.
Please do.
It honestly sounds like a sci-fi doomsday scenario.
Yeah.
It sounds like a Hollywood disaster movie script designed to scare people. Is this just theoretical math? Are we just sitting around scaring ourselves with worst-case computer models, or do we have actual physical proof that modern tech can't handle solar storms?
That is the most important question to ask, and the answer is that it is absolutely not just theoretical math. We are not guessing. The sun has given us previews.
Previews.
It has provided clear, undeniable demonstrations that our modern infrastructure is acutely, dangerously vulnerable to geomagnetic storms.
Let's talk about those previews, because they take this out of the realm of theory and put it right into recent history. Start with what happened in 1989.
In March of 1989, a severe solar storm hit the Earth. Now, it is crucial to note for context that this storm was far weaker than the Carrington Event.
Okay, so a smaller storm.
Right. It was a significant storm, but not a civilization ender. But when the plasma cloud struck the magnetosphere, the fluctuating magnetic fields induced massive currents in the northern hemisphere, and those currents flowed directly into the power grid of Quebec, Canada.
I was reading about this, and the geology of Quebec actually played a huge role, right?
Yes, that's a brilliant point to bring up. The Canadian Shield is a massive expanse of igneous rock, which is highly resistant to electricity.
Right.
So when the massive electrical currents were induced in the Earth's crust by the solar storm, the rock resisted the current. The electricity, seeking the path of least resistance, flowed up through the grounding wires directly into the massive transmission lines of the Hydro-Quebec power grid.
Wow. And what happened when that massive influx of space weather hit their grid?
It was almost instantaneous. In just 90 seconds, the entire Hydro-Quebec power grid collapsed.
90 seconds.
The massive transformers began to saturate and overheat. The grid's automated protective relays, sensing the catastrophic imbalance, tripped to save the transformers from completely burning out. As one massive line shut down, the load transferred to others, overloading them in milliseconds, and the entire system cascaded into total darkness.
90 seconds.
90 seconds from normal operation to total blackout. Roughly 6 million people were left completely without power in the freezing cold of the Canadian winter for over 9 hours. Traffic lights failed, the metro shut down, airports closed. Some remote areas were without power for several days while the grid was meticulously restarted.
A storm significantly weaker than the Carrington Event took out the grid for 6 million people in a minute and a half. That is a terrifying proof of concept.
It demonstrated beyond any shadow of a doubt exactly how quickly geomagnetically induced currents can overwhelm modern, interconnected, alternating current power systems. The grid is a delicate balancing act of supply and demand, and a sudden massive influx of DC energy from the sky can tip it over into failure almost instantly.
But the 1989 event in Quebec, as bad as it was just a preview of the mechanics. It wasn't the big one. Which brings us to the absolute gut punch of this entire deep dive. Because the big one, a true Carrington-class superstorm, isn't just a historical artifact from 1859.
No, it's not.
It isn't just something that might happen in the distant future. It's something that almost happened to us right now in the modern era. Take us to July 23, 2012.
The event on July 23, 2012 completely shifted the paradigm of how astrophysicists view solar threats. On that day, the sun unleashed a coronal mass ejection that was truly massive. Fortunately, we had a satellite called Stereo-A orbiting the sun, which was perfectly positioned to measure the eruption.
And what did the data say?
The data was unequivocal. Observations confirmed it was a Carrington-class superstorm. It was a billion-ton cloud of magnetized plasma traveling at extreme speeds over 6 million miles per hour, carrying an incredibly strong southward-pointing magnetic field. It had the exact kind of destructive potential we've been discussing.
And it tore straight through Earth's orbit.
Yes. It crossed the exact path, the exact invisible lane in space that Earth travels along as it orbits the sun.
So I understand the orbital mechanics here. We essentially blindly walked across a set of train tracks, and a cosmic bullet train moving at 6 million miles an hour missed us by inches.
That is an excellent, if chilling, way to conceptualize it. The Earth is a moving target, traveling along its orbit at roughly 67,000 miles per hour. The sun fired this massive, civilization-threatening superstorm directly across our track, but we only missed taking a direct hit because the Earth had already moved past that exact spot in its orbit.
I have to ask, by how much? How close was the call?
We missed it by about 9 days.
9 days.
If the solar eruption had occurred just 9 days earlier, a microscopic blip in the grand scale of the solar cycle, the Earth would have been directly in the crosshairs. We would have taken a direct, square hit from a Carrington-class event.
9 days. In the grand scale of planetary orbits, in the billions of years of the solar system's deep time, 9 days is a microscopic fraction of a margin of error. It is essentially a coin flip. What would have happened if it had hit us on July 14th instead of July 23rd?
We don't have to guess. A highly respected researcher from the University of Colorado, Daniel Baker, who extensively analyzed the Stereo-A satellite data for NASA, put it very bluntly. He stated that if the 2012 eruption had hit the Earth, we would still be picking up the pieces today.
Seriously.
The global damage to the power grid, the destruction of orbital satellites, and the subsequent collapse of the digital economy would have been so severe that global recovery would be an ongoing, multi-year, or perhaps multi-decade, agonizing process.
That is the ultimate definition of a near miss. And frankly, it completely recontextualizes the threat for me. Because it's not a theoretical question of if the sun can still produce these massive storms. It clearly can, and it just did a decade ago. It's purely a game of cosmic roulette.
It really is.
It's a question of whether we happen to be standing on the tracks when the train comes through, which leads us to the statistical odds. Because after 2012, we aren't just guessing about the risk anymore.
Exactly. The 2012 near miss prompted a massive surge in risk analysis. Scientists and actuaries have attempted to quantify that risk by looking at historical data, analyzing the frequency of sunspots, studying solar cycles, and observing the rate of smaller, non-Earth-directed events. Researchers have developed statistical models to estimate the probability of a future strike.
Yeah, and what did they find?
One widely cited published study, led by physicist Pete Riley, estimated that there is roughly a 12% chance of a Carrington-scale event hitting Earth in any given decade.
Let me do the math on that. A 12% chance per decade. That's roughly a 1 in 8 chance.
Yes. Now, we must frame this carefully. It is an estimate. It is a statistical probability based on currently available data, not a universal, infallible consensus. Some researchers might look at the data and argue the odds are slightly lower, perhaps 5% or 10%, while others might find them higher.
Ihr Stück.
But the core takeaway is the sheer magnitude of the probability. A 1 in 8 chance per decade is an alarmingly high probability for an event that could cause trillions of dollars in damage and fundamentally disrupt the mechanics of modern civilization.
Yeah, if you told me I had a 1 in 8 chance of my house burning down this decade, I would buy so much insurance.
It's a risk level that, if applied to an asteroid strike or a massive earthquake, would demand immediate, globally coordinated, and massively funded defensive preparation. Yet because it's invisible, it largely remains a niche concern.
And just when you think you've wrapped your head around a 12% chance of repeating 1859, there is a final layer to this deep dive, a deep-time chill that really puts our place in the universe into perspective, because we've been talking about the Carrington Event as the biggest storm in recorded history.
Recorded history, exactly.
But recorded human history, especially recorded astrophysical history, is incredibly short. We've only been seriously looking at the sun for a few centuries. What happens when we look deeper into the past, before telescopes and telegraphs?
Well, when scientists want to look at solar activity before the invention of modern instruments and historical records, they can't look at the sky. They have to turn to the Earth.
What do they look for?
They look at ancient tree rings and deep ice cores drilled from the poles. These natural archives trap chemical signatures from the atmosphere year by year. Specifically, scientists look for spikes in a radioactive isotope called carbon-14.
Okay, I was reading about this and I couldn't quite wrap my head around it. How does a solar storm on the sun end up leaving a chemical footprint inside a piece of wood 1,000 years ago?
It's a fascinating chain reaction. When an extreme solar storm hits the Earth, it bombards our upper atmosphere with high-energy solar protons. When these protons collide with the abundant nitrogen gas in our atmosphere, they trigger a nuclear reaction.
Like literally changing the atoms.
They knock a neutron loose, converting stable nitrogen-14 into radioactive carbon-14. This freshly created radiocarbon rapidly oxidizes to form carbon dioxide, and what breathes in carbon dioxide? Exactly. The trees absorb this isotopically heavy carbon dioxide during photosynthesis and lock it into the wood they're growing that specific year. So if scientists find a sudden, massive spike of carbon-14 in a single specific tree ring from a known year, it indicates that the Earth was bombarded by extreme solar radiation at that precise moment in history.
They're essentially a natural physical recording of the sky's history.
They really are.
That is brilliant. So by analyzing these ancient tree rings, scientists have discovered evidence of solar storms that actually dwarf the Carrington Event. And the most famous of these is known as the Miyake Event, discovered by a Japanese physicist named Fusa Miyake, which occurred around the year AD 774.
Yes, AD 774, well over 1,000 years ago during the European Middle Ages. When Dr. Miyake and her team analyzed the rings of ancient Japanese cedar trees, what they found was staggering.
What did the tree rings tell us about the sheer scale of the Miyake Event?
The carbon-14 spike associated with the year 774 is massive. It is an abrupt, vertical leap in the data. When they calculate the amount of solar energy required to produce that much radiocarbon in a single year, it indicates a solar proton event, a solar storm that was significantly more powerful than the 1859 Carrington event.
How much more powerful?
Estimates vary, but it could have been an order of magnitude 10 to 100 times stronger. It provides definitive, physical, undeniable proof that the sun is capable of producing storms vastly bigger than the one that set the telegraphs on fire.
The sun has done worse.
It has done worse, and according to the laws of probability and astrophysics, it will inevitably do worse again. The Carrington event is not the theoretical maximum of the sun's power. It is merely the largest event we happen to have witnessed with modern observational tools in our very brief window of technological history.
Right.
The Miyake event proves that the ceiling for solar destruction is much, much higher than we ever thought.
So, bringing all of this full circle, we started this deep dive looking backward, right? We looked at an echo of the past. We looked at rugged gold miners making breakfast in the middle of the night, at Richard Carrington meticulously sketching sunspots in his quiet observatory, at frantic telegraph operators getting knocked out of their chairs by the sheer power of the sky.
It's quite a story.
But most echoes of the past are just sounds we look back toward. They are history lessons. We study them to understand where we came from.
But the Carrington event is fundamentally different from a standard history lesson.
It is entirely different. It is a recording of something that is actively, inevitably headed back toward us right now. It wasn't just a quirky historical story about 1859. It was a rehearsal.
A cosmic drill.
The universe ran a drill to show us exactly what the physics of a coronal mass ejection can do to human infrastructure. And the terrifying part is we simply do not know the date of opening night.
We understand the mechanics of the sun, we have mapped the extreme vulnerability of our modern grid, and we have calculated the statistical odds. We are simply waiting for the orbital alignment to match the solar eruption.
And here's the thought I want to leave you with. The
Yeah.
paradox that has been sitting with me since we started researching this. We are currently facing the massive existential threat of climate change. And to solve it, we're aggressively transitioning away from fossil fuels. We are building massive solar farms, wind networks, and pushing for widespread electric vehicles. To make that green transition work, we are actively expanding the electrical grid, making it wider, making it smarter, and making it more deeply interconnected than ever before.
Which is necessary.
It is entirely necessary. But by building the ultimate green, hyper-connected grid to save ourselves from the Earth's changing climate, we are simultaneously building the largest, most efficient, most delicate antenna in human history to catch the next storm from the sun. The very solution to one existential threat is actively constructing our ultimate vulnerability to another, something to mull over the next time you look up at the sun or plug in your phone.